Hello students, welcome back. We just completed section 4. But before going over to section 5, let's have a brief recap here. In section 4, we studied factor groups in 2 stages. First, a special case, when we started off with a homomorphism and its kernel. And please recall that all kernels are normal, so this is indeed a special case. And under this special case, we can define the factor group G over K, where K is the kernel and G is the starting group. And that happens to be isomorphic to the image phi of G, which is a subgroup of G prime. Remember all that? In this particular case, we call this factor group G over K as a factor group of G modulo K. And then we studied the general case. We established a factor group G over N for arbitrary normal subgroup, not necessarily associated to any homomorphism or any kernel. So this is far stronger and more general, but it comes with a catch. In this case, we had some guidance. Isomorphic to something, and that came from homomorphism, and it was induced from the original group G. But then again, in this case, we have the factor group, yes, G over N, and then what? Well, that's the question we want to answer in section 5. And then what? We want to get something like this. So we want to express, rather re-express everything in terms of homomorphism again for general case. That's what we are up to in section 5. Okay, step 1 of this problem is for the normality itself. It's a bit of a side note or warming up, but still it falls into the same category, re-expressing everything in terms of homomorphism. And in this case, we're going to use this particular homomorphism as a main tool, which we call the inner automorphism. You can prove that this is a homomorphism. This computation, G actually inverse, this thing is called a conjugation. This kind of operation is called a conjugation. And it's obtained by this conjugation, by G, and this kind of computation preserves the group operation. You can actually prove that. The detail is left to the students. And then, moreover, this is an isomorphism from G to itself. It's 1 to N and R to N homomorphic. And that kind of thing is called an automorphism. And this particular automorphism is called the inner automorphism. And in terms of this inner automorphism, we can redefine the normality like this. A subgroup H of G is normal if it is invariant under all inner automorphisms. What do you mean by invariant? This one right here, which I just highlighted in blue. The set stays as itself. Here, the set stays as itself. The elements here, each element of H may move around, but within H. It's shuffled within H. And then the set itself stays the same. And that applies for all elements G of capital G. Then we say the subgroup H is invariant. Excuse me, I said it wrong. Then the subgroup H is a normal subgroup of G. So H is normal subgroup of G if it is a subgroup that is invariant under all inner automorphisms. And please recall that. And if I put in this definition of the inner automorphism, then we get the very same expression as the normality that we considered in section 3. And speaking of section 3, do you recall that we reduced this into an inclusion like this? This thing is called quasi-invariance. So basically half invariance. And that's because only half of the equality is true, only half of the equality has to be true. This inclusion is true. The other inclusion may or may not be true, but as a matter of fact, we can prove it because of this, the red part. Remember that? We did it in section 3. The key part is this one, which I just highlighted in red. It works for all G of capital G. And by the way, here is the element expression of the same thing. So what did he just do? We redefined and re-expressed everything about normality in terms of homomorphism, using the inner automorphism as a main tool. As I told you before, this is more or less a warming up, because it's not directly related to what we are going to do next, but it's not just a side note, because it falls into the same category or the same philosophy, re-expressing everything in terms of homomorphism. But then again, the real deal did not begin yet. It begins now. 5.2, canonical homomorphism, which is defined like this. Let N be a normal subgroup of G. Then the map gamma from G to the factor group G over N defined like this. Gamma of X is the coset Xn. This turns out to be a homomorphism with kernel N. Let's come back to this. This map is well defined. No problem about that, because it is defined in terms of each element. For each X in G, we can define it like this, as a coset, which is a member of the power set. Now, is this a homomorphism? And also, it's the kernel, just N? Well, let's see. This one first, homomorphism part first. Well, what is this gamma of xy? By definition, this is x times y, n, isn't it? Yeah, that's the definition of gamma. And then gamma of x is xn, and gamma of y is yn. So that's what this purple thing is talking about, this one here. Is this true? Of course it is true. That's the very definition of the group operation in the factor group G over N. It works because N is a normal subgroup. In general, it doesn't work, but for normal subgroups, it works. And that's reproduced in terms of a homomorphism, gamma. Okay, one down, one more to go. How about the kernel? What is kernel? It's a preimage of the identity element. Remember that? But what's the identity? Well, identity for the factor group here is just N. So this identity is just N. In other words, this is set of all elements in G such that gamma of X is the identity. But then again, what is gamma of X? Well, it's defined as Xn. So Xn is equal to N. When does this happen? When does this happen? This is hardly an emphasis. Okay, there you go. That's argument conspicuous. When does that happen? That happens when X belongs to N. When X belongs to N. Well, here's the proof basically. The first and the second. Xn is N if and only if X belongs to N. Simple observation, the details left to the students. So we prove both. So this homomorphism defined like this, each element is going to a coset generated by that particular element, is a homomorphism with kernel n. This homomorphism is called the canonical homomorphism or the natural homomorphism of the factor group G over n. And I may end up using some alternative terms, canonical projection or natural projection from time to time, because when this thing is applied in geometry, some analysis too, but mostly in geometry, it takes the form of projection most of the time. So many people call these as projections, but I'll try to follow the notation from the textbook. So I'll try to call it canonical homomorphism or natural homomorphism. One comment here. Through this canonical homomorphism, we ended up getting this normal subgroup n, which is arbitrary normal subgroup, as a kernel. So, can we use this to go back to 4.2 and define the factor group accordingly as a kernel? The answer is actually no, you can't do that. There's a bit of a problem here because in 4.2 we used the kernel concept in the homomorphism to define this factor group G over K. But here we have to define the factor group G over n in general first in order to define this homomorphism, which has n as the kernel. So this actually doesn't work. We have a circular logic. Can we still have some form like that? G over K is isomorphic to phi of G. So you see, according to 4.2, let me keep those in the same viewing window. We have G over K is isomorphic to phi of G. We get that. Can we get something similar here in 5.2? This one, yes. Let's rewrite all those in terms of the characters we use here. G stays as G, K becomes N, and phi is replaced by gamma. So in terms of this, we get G over N is isomorphic to gamma of G, according to this. And now, is this true? Well, we can prove that. But we cannot go back to 4.1 and then redo it because of that circular logic I told you before. So we have to reprove it, reestablish and reprove it for the general case. And that's the next topic here. So it works for this gamma, but for other homomorphisms too. So let phi be a group homomorphism from G to G prime with kernel K. And as I had before, if we have the special case gamma, then kernel is n. So this is more general case that includes 5.2. Now in this case, this map defined like this is an isomorphism, which we call canonical isomorphism or natural isomorphism. That's the next step. So how do you do that? Well, we don't have enough time, so we'll do that in a separate video. But I hope you see the connection here. This is similar to what we did in 4.2, but we are redoing it because we want to establish everything in general without the trap of that circular logic. So that's what we are up to, and we're going to continue that in the next video pretty soon. See you soon.